All right. Well, it looks like most people are here, and we're on our own. So I guess I will just get started. So what's the point of today? So in the last class and plenty of lectures now, we've seen a bunch of operational semantics, and we can talk about things about those. Right? So I kind of just rewrote it on the board here. We already saw pretty much this top half of the board, where we have some actual rules of reducing individual terms. We figured out that that's not enough. We have to at least be able to reduce in these contexts called the evaluation context if we're ever going to hope to get an answer in general. Otherwise, we'll get stuck randomly all over the place. And the other step, which is kind of implicit, but I'm just writing explicitly here, it's called, this is an operational semantics. This is technically a small step operational semantics, which means each of these steps doesn't do a lot, so I'm going to need a lot of them to compute the final answer, right? So a single arrow is not enough, so I'll need a bunch of arrows to get there. And so I'm just explicitly writing here. Different people have different notations. Sometimes people will write the Kleene star, right, which we've seen a bunch in the Kleene algebra lectures, which means a repetition of 0 or more. I've written it explicitly as inference rules here, right? So just like we do for typing derivations, we can do that for reductions, right? So what is this saying? There's 3 rules. The first one, I put little shorthand names. What is this saying? If I can take one step, then that counts as taking 0 or more steps, right? That's more specific. So clearly, one step is a special case of 0 or more steps. What's this? I don't have to take any steps, right? So I'm writing this as a maps to arrow with double arrow heads to signify that there's a bunch of arrows all stacked up. So I don't have to take any steps. What's the common name for this word with the hint on the board? Right? Reflexivity. And then if I take some steps, and then I take some more steps, starting where I left off, then I can get there in one chain of a bunch of steps, and this is transitivity, right? So all I'm saying is that, and this is going to be a typical thing, I'm not going to repeat these a ton, right? But I'm saying that this double-headed maps to arrow is the reflexive transitive closure of the single arrow, right? Which means you can do the single arrow, and you also have these reflexive transitive closures. And of course, the single arrow itself has this other rule. I'm giving a name to it now, foreshadowing for something in a little bit. But this is, sometimes you can call this compatibility with evaluation context, right? This is if I can take a step, then I can also take a step on a subterm as long as it's surrounded by an evaluation context, right? So this is just the quick recap of what we already saw. And now I don't want to talk about this so much anymore, but to build some more reasoning on top of that, yeah.
Is the step beta different from a regular step?
I'm annotating these with beta also to foreshadow some stuff, because otherwise the notation will become a little confusing. So I'm just saying these are all the beta steps. And I specifically named all of these rules with beta. Kind of like when typing rules, we have a whole bunch of introduction rules that all start with I, right? And so there's going to be different kinds of things that I could do that are not beta, and also different things that I could say about beta, right? So I'm just saying these are one of the beta steps, and I'm writing it specifically on the arrow to annotate which step I'm doing. I could be even more specific and say this is beta bool 2 if I really want to do that in beta arrow right there. But we're going to get to that in a second. So don't worry too much about that notation. If you were looking at the notes, then I also, for the most part, put the beta on it to make that link, which we're about to do just now. Yeah?
Do you think you could repeat that question?
Oh, sorry. So the question was, why did I put beta on the arrow, more or less? Right? I'm just sort of explaining we're about to introduce more relations between terms that are not typing relations, necessarily. Right? OK. Yeah?
So I guess the beta in the conclusion of the compat rule should not.
Oh, yeah, you're right. I probably should do beta here if I want to really, I'm saying a bunch of these beta steps. I want to be really specific. Let's move on from the notation for a minute till we get to the actual interesting thing, and I think it will motivate that as we go. OK, so I don't want to talk. So what does this say? This just says, how do I run the program and get the answer in a deterministic way? We didn't talk about the fact that it's deterministic, but this reduction relation has the property that I can only take one step or none, right? There's no really other place I could go. The idea is to model what a computer does, which is not very creative. It always just does one thing deterministically, right? Unless you insert some external randomness, which we're not modeling here. So there's only one choice. But now I want to ask the question of when are two terms or two programs equal, right? When are they the same? Right? So let's start with some examples. Is true equal to false? No? Why not?
They terminate with the different values?
They terminate with different values, right? So that's good. So it's not equal. They terminate with different values. It's kind of foreshadowing another question, which is going to be, let's say I have a not function. So not is going to be a function that takes one parameter, right? So how do I implement not if I have if then else? I can check if this is true or false and then return the other thing, right? So if x is true, then I return false. Otherwise, I return true, right? So is it the case that false is equal to not true? Right? So you kind of already got to the punch, right? So if we kind of run both sides, I get the same thing. So this is just itself. This, if I take a few steps, I'll reach false. So, I mean, it looks like they should be the same. And how do I know? So this is not equal. The operational semantics tells me I can just run the two terms, and they'll get the same answer, right? So I somehow have to run both sides to get the same answer. How about this one? Is false equal to and false with x, right? So and is, let's just say, the obvious and function. But what do people say here? No, why not? So someone want to argue why it is equal or not equal? Yeah.
You have one program that terminates and one program that doesn't.
Ah, it doesn't terminate. So why doesn't it terminate? So I haven't defined what and is.
We don't have a value for x.
We don't have a value for x. So I'll write it like this. Let's write the and function, and of x. Well, let's do it the other way around, because I wrote an x there. Y and x. If y, then, so if y is true, we return x. Else, we return false. All right, because if y is false, false and anything is false. OK. So if I start here, and I start applying the operational semantics, I get to false. So I didn't actually say that everything has to be closed. So I'm going to try to take the most permissive philosophy that unless something actually goes wrong, I'm going to allow it. Right? So rather than come in with a whole bunch of preconceived notions that it has to be like this or that because that's the way I like it, I'm just going to say, well, I mean, the rules work fine. If you look at chapter 1 of the notes, there's a whole bunch of 100 years of theory on why we can deal with open terms, right? Terms with free variables in it. And, well, so if I run this, I actually get to an answer. But what about false equal to and x and false? So this one, I can just run the operational semantics, and it works. What about this one? Yeah.
It's not equal.
Yeah. Well, I can't run it, right? I'll get stuck at this point. So when I plug in, you know what? Let me just call it y for consistency to make it easier. When I plug in y for y, So we're not doing weird renaming shenanigans. And I have to know is y true or false, right? So the operational semantics is not enough to deal with that. But morally speaking, should they be equal? What do I mean by that? Well, if I'm going to be type checking these things, then what could y be at the end of the day? It could be true or it could be false. And in either case, this works. And in either case, I get false. So it should work, right? But the operational semantics is not enough, right? And so part of the idea of today is we can do a lot better than the operational semantics. Just saying, well, I just ran it and it didn't work, so I guess they're different, is probably not the end of the story. And we can probably do something a little bit more clever. So let's do another version. Is lambda x and false x equal to lambda x false. So here, I could just run both sides directly, get an answer. What about right here? This is a question mark so far. I can't run them, or if I do, I just get two different lambdas, and the code is different. So that doesn't tell me anything, right? So that's another question. And let's do probably the most interesting one. Not x, is this equal to the identity function, lambda x, x, right? And I kind of said before, right, same reasoning as here. If I plug in true, it works. If I plug in false, it works. If I plug in a function, I get stuck and it's terrible. So maybe it sort of kind of works, and maybe it doesn't. But the questions I kind of want you to think about is, what does it really mean to be equal, more than just, I tried to run both closed terms, and they're the same thing. That's the most boring version of equality. And then how do we answer these questions and effectively answer these questions? So actually have a technique that I can generate these in a reasonable way, these equalities, right? So that's the overall goal here. And let's look now at, well, there's both of these, right? So to run this program, where y is the free variable I don't know, I somehow need to plug in a value for y. This is kind of reminiscent to what Amal was doing with logical relations, right? The idea of, if we want to say things about open terms, one way to deal about that is say, well, what are all the substitutions that if I can plug in for that? So then I kind of close it off, in a sense. But that doesn't really help me here when I've got two functions. And in a sense, what I really want to do is just like run the body of the function. If I just run the function code and get somewhere, and if comparing the insides of the code give me the same result, then probably they should be the same function, right? What else could go wrong? But actually proving that's a little bit tricky, right? So, but why would they be the same? Well, in this case, I would say, no matter what context that this function might appear in, what's the worst that could happen? I might call it and pass in an argument. And here, literally, no matter what I pass in, I can pass in functions for x, I can pass in bananas, it doesn't matter. Technically, if I follow these rules, it will get to false on both sides, right? So the worst thing that could happen is I include this function in a context, which will call it one or more times. And each time I pass something in, and every time, it's going to get false on both sides as a result. OK, so well, the goal here will be, how do we define that notion formally? Then how do we, like I said, actually prove these equalities in a reasonable way? So I'll now start with the first kind of definition here, which is going to be observational or contextual equivalence, right? Which is that idea that two expressions or two terms, they're sort of a fragment of a total program, of a whole program. So no matter what context that you're embedding them in, no matter how you complete the rest of the program around that difference of term, I end up with the same result. That's the idea. OK? So here we're going to have a definition of equivalence. Also known as contextual, right? Both are pretty reasonable terms for this. So let's start defining them. I'll define them in pieces. And at first, I'm going to start with just what's on the board without involving types, and then see what kind of leverage types gives me afterwards. All right? So how do I say, and I'll do this in kind of 3 steps because this is a typical way to break it down to make it a little bit less of a mouthful at any individual step. So I want to say when is M contextually equivalent to N? Right, so I'll use the approximation squiggly equals signs. So when is this the case? So M is contextually equivalent to N if and only if M approximates N and N approximates M. I'm kind of cheating right now. It's like, OK, fine, but what's approximation? Right? And I'm just saying equivalence should be a symmetric thing. And actually stating that can be a little tricky. So I'm going to do an asymmetric one and say it works both ways. Right? So this is the idea of everything that M does, N will do. And everything that N does, M will do. That's the idea. OK, so this is where the actual meat is. So when does it happen that M approximates the behaviors of N? Or it's contextually, this would be an observational approximation of N. So if and only if. And well, I'll just kind of write it this way. So for all C in the set of contexts, so I'm not going to spell out. So technically, this is another BNF grammar. What do I mean by all the contexts? So these are evaluation contexts. They're a set of terms with a box in them. And there's rules on where that box can appear. When I say the set of all contexts, I mean put the box anywhere you want. I really don't care. And as you imagine, there's a lot of rules saying that the box could be anywhere, and I don't want to spell them all out. If you're interested, they're in the notes how to spell that out. But it literally just means take any term, then highlight part of it, delete it, and replace it with a box. Anywhere, no restrictions whatsoever. Right? That's kind of the intuition. OK. So give me all of the contexts. So if for any context such that it closes the 2 terms, right? We have that issue of open stuff, right? Sometimes you can get away with leaving these open, but I'm just going to put the closure thing in just to make everyone comfortable. So what do I mean? So I mean if you fill, and there's different ways you can specify it, but I'm going to be a little bit observational about this. So if you plug M into C, if you ask what are the free variables of C surrounding M, that is the empty set, which is the same thing as the free variables of C surrounding N, right? So C closes over all the free variables in these 2 terms, whatever they are. So when I plug it in, I no longer have any free variables. OK, so for all the contexts that close over M and N, then if running M, I get to some value, right? Then there exists some other value such that N will reach that value. And these should be beta reductions. And V is similar to W. OK? So this is sort of why it's asymmetric, right? Well, I'll get to the asymmetry in a second. But there's one last bit of when are 2 values similar, right? So I just kind of keep pushing the problem down. This is the final step. When are 2 values finally similar? Comparing 2 things. So this is going to be the smallest relation with these facts. True ought to be similar to true, kind of like what we're talking about. False is similar to false. I will say true is not similar to false, which is why these are not equal, right? They should be different. And there's one other thing I should probably say. What's another form of value we might run into? Lambdas. So lambda, I might have two lambdas. When are they similar? And we kind of were doing this with logical relations. We have to say some properties about the body of the code. I'm going to say it's a very shallow property. Any two lambdas are similar. Do not care. As long as they're lambdas, they're similar. And you'll think, that's a little weird, but we're already closing over all of the context. So if I say the two lambdas are approximately the same, then that means they have to be the same for all the contexts, including ones that call them and plug stuff into the arguments, right? That's kind of where we get away with this. At the end of the day, it's sort of, I run my interpreter, and like let's say I'm doing scheme, because it's also an untyped kind of lambda calculus thing. I might run it, and it'll say hash t, and I might run it and say hash f, and that's obvious what it is. Or I run it, and it says procedure. I can see that it says procedure, but I don't know anything about the code unless I called it. So certainly, if that's similar to something else, I should be able to take that procedure, embed it in a context where I'm actually calling it, and I'll inspect the outputs. That's fine. But I can't really say anything at that moment, so I kind of am giving up right there. OK, so that is the whole definition at this point, right? I kept pushing it down. So similarity is about values, and we're just looking at the very top, like a very like false is not the same thing as a lambda. I'm just saying that, and I think you all believe me. It's also not the same thing as true, but true should be the same thing as true, right? And then why is this property not symmetric? Not necessarily. We have a counterexample we already saw. What about non-termination? Right? So if I say, right, and here's a nice fact that we saw omega. That's the lambda calculus term, right? I don't have to worry about types. We've got omega. What was omega? Omega equals lambda x, x applied to x, applied to lambda x, x applied to x. That never terminates. So if I have omega here, and I ask, is omega an approximation of any n? Yeah, I mean, because, sure, I mean, you can probably find closing context, but it never finishes, so I never really have to say anything, right? But you might guess that there are certain terms here, like true, which are not, right? So omega is less than true, and it's less than any n, but true is not an approximation of omega, because it does finish, and omega never finishes, right? So the natural way to do these things is kind of asymmetric, and when you have effects, when you have non-termination, that starts to matter. So I'll just say the equivalence is going to be it works both ways, and that will save us a little headache later. All right, so this, I would say, is the gold star standard of what it means for two terms to be equal without involving types, right? If I don't know anything about types, this is the gold star standard. But oh boy, is it really hard to use, right? Well, if you tell me two things are contextually equivalent, that's great. I learn a lot. If you task me to prove that these two things are contextually equivalent, you're doing a generalization over all possible contexts I could ever write in the program, and then I now have to show somehow that they're all equal. This is not the easiest thing to do, and if I want to generate hundreds of little program equalities, you can imagine how tedious and terrible that would be, right? So the goal of what I want to do next is to introduce a technique that is far easier to use, but is an approximation of observational equivalence, right? So this is kind of that soundness principle. If you use some syntactic methods of rewriting, then it's very easy to check that it works. You just look at the individual steps and you say, yeah, I mean, everything lines up. But you know if you use those rules, they will be contextually equivalent, because that's what we actually care about. OK, so let us get going. And I'm going to introduce now more arrows, more relations. Right? That's why I had beta here. So I want to say that they're somehow related, but in different ways. And there's going to be a few of these. So let me pull them up. So I think, yeah, OK. So this is my operational semantics. I can only reduce in evaluation contexts. Now I want to introduce the idea of a general reduction. Right? So I'm going to have a general reduction arrow. It doesn't have the little tail on it. And this is going to be the fully compatible closure of the operational semantics. And what do I mean by that? Well, that means if I can take a step by the operational semantics, then, oops, I forgot the entire point. Then I can do that in any context. Right, so it's just like that rule, but now instead of saying it has to be an evaluation context, I'm saying literally do it anywhere. Look at the entire term. If you spot something that looks like the left-hand side, replace it with the right-hand side, no restrictions. Right? You might obviously get a little nervous and say, what if something goes wrong? And that's why we're going to prove that each one of these steps it preserves observational equivalence, right? So we don't actually break the final result of the program, right? So we're doing things very out of order at this point, right? Typically, I'm doing things in advance of when I would normally be doing them, right? So this says out of order execution is OK. Then one more. So that's the single step. Unsurprisingly, this is going to be the reflexive, transitive closure of the single arrow, right? So if I put two arrowheads, I just mean a bunch of steps, right? It's like basically those reflexive. So you don't have to do anything, and you can do more than one thing, right? And you can do reductions in any context. And finally, one more step is beta equivalence is the symmetric reflexive transitive closure of a single step. Whoops. OK. So the operational semantics is defined inductively. These things are defined inductively, which just says apply a rule anywhere, do it however much you want, and then finally, you can go forwards and backwards. I don't care, right? So any direction. So this is the symmetric closure. And the idea here, of course, is it's much easier to use these in the sense that this is high school math, right? So when we are in high school and we learn math, right, we have numbers and arithmetic operations. We learn properties on how those work. And then you'll look at this big, long formula. And then you'll just start rewriting stuff wherever. And you might expand. You might contract. You'll do it in any subterm. This is actually what we're familiar with. And now we're saying do it to programs. Why not, right? So that's all it is. This is purely syntactic writing. I'm not doing anything fancy here. Just look at things that look like stuff on the left-hand side, replace it with the right-hand side, however you want to do. OK. Now, the challenge is going to be, how do we prove that this random rewritings that I just told you to do doesn't mess up the results of my program, right? And so I'm going to start with a technique that doesn't involve types at all, right, which is some properties of rewriting systems that we can just do it just based on looking at these rewriting rules. We can prove that using some sort of standard theorems. And then hopefully there'll be time to introduce types and get some new equations that we don't have before, so we can actually prove things here. Oh, by the way, I can fill this in. So no, that's still a question mark. But this is, right, these two sides are equal by the rewriting, which, what do I mean, right? I can reduce the two sides in any context, including inside the body of a lambda, and then they both look like the same term, right? So if you want to kind of get some practice, you can do this yourself. right? But kind of prove just with this idea that we have the symmetric, reflexive, transitive closure of the compatible closure of the operational semantics, which means do it anywhere, however you want. OK. So now I want to talk about how do we kind of relate these things. And so we're kind of there. I'll say we've got this kind of implication, which is by definition, right? Which means if I do something in the operational semantics, it obviously works here, because this is a strict generalization, right? That's a special case. And clearly, this is also, right? I'm kind of one or more, right? And if I can just apply rules in the forward direction, that's a special case of equality. I just don't use symmetry at all. Right? So this implication follows by definition. This idea of observational equivalence is only about the operational semantics. So I want to go the other way. I want to say, if you use this rewriting theory, it says something about reductions in general, which is not totally obvious, right? Because even if I don't worry about the operational semantics, the reductions can go forward and backward. How do I know that if two things are equal by arbitrary forward and backward rewriting, that has anything to do with only the forward direction? What would that be? And the trick here that we're going to use is confluence. Lets me prove something like that. Obviously, it doesn't totally work. If two things are equal, I don't know that the first strictly reduces to the second, obviously. But maybe they can reduce to a common subterm. And then I only have to do one alternation. And that's maybe the more comfortable one. And then I'll say general reduction to that operational semantics up there. This is going to be standardization. Okay? Which will say if I can calculate an answer using this general unrestricted reduction arrow, then I can calculate a similar enough answer using the operational semantics. Right? I'll talk about what are these properties and how do we sort of prove them. I won't go through the full proof because that's an entire other lecture series. Maybe if we have another lecture series, I could do that. But for now, I can just tell you the shape of these and kind of how they go and why they're a little bit trickier. So who here has heard of confluence before? I think maybe we were seeing that in the previous lectures, some things about confluence. What about standardization? That one's probably the less familiar one. If I asked you, write down the theory, theorem of standardization, you might be a little bewildered. All right. So let me do it here. And I want to try to start by motivating these things and then kind of show how it goes into it. So confluence, what's the point of confluence? Well, if I think in general, suppose I have two terms. I don't want to get too wild here. M and N. And they're equal by doing beta rewriting. And they're equal in this particular way. Right? So, OK. Right? So what do I mean? What I mean is, if you ignore the two-dimensional aspect, I've got this term M. I kind of had something that it reduced from, so I expanded a bit, and then I contracted a bit. And I expanded a bit, I contract, until eventually I reach N. And hopefully, you can at least believe for now that every equality is some alternation of forward and backward reductions like this. OK? So how do I show that they both reduce to the same term? And this is where the property of confluence comes in handy. So this is the square of confluence. If I start somewhere and go apart, however much you want, it eventually comes back together to some common subterm. That's what the property is. Right? So if I have confluence, that means this first split, right, where I've kind of written them so that splits go downwards and joins also come back downwards, then that means I can bridge the gap and join these 2 points together. Same thing here. Right? This is confluence. And then same thing here. I'm not bothering to name these intermediate terms because there's a lot of them. So just imagine there's M1, M2, blah, blah, blah in between. just intermediate terms. Okay. So what? Well, one thing to notice is compared to here, right, how many splits did I have? I have 1, 2, 3 splits. How about here? I have 1, 2. Right, so this has 3 peaks, and this one only has 2 peaks. Right, this is, I'll write it here, this 1 peak, 2 peak. So I've reduced the number of peaks. So if I do it again, if I start applying more confluence, I go from 2 peaks to 1 peak, right? And then if I do it one last time, I eventually get to a point, right? And so what is this property? This says that if I have m equal to n because I did reductions back and forth, as long as my reduction rules are confluent, having this property, then, so this is the theorem, if m is equal to n, then m reduces to something that n also reduces to, and this is for any confluent reduction arrow, right? As long as I know, I don't really care that it's beta reduction at this point, as long as it's confluent. I have this property that syntactic equality, doing reductions in any order, I can always replace that to conversion to a common term, right? So that's the important property and why we care about this confluence thing. Where do I want to do the next part? Probably here. Okay, so our goal, right, if we want to relate equality to reduction, I can say, well, if this reduction is confluent, then equality always can be replaced with conversion to a common subterm or a common reduct. Okay, so that's the confluence property. How do we prove it? Right, so confluence, right, is this property that, you know, if I take this diamond, so this is confluence. As you could imagine, proving that directly is really hard. How come? Because I have many reductions in both directions. And that means I may have reduced some things which have introduced other future reductions that I've reduced those. That's really hard. But what's something a little bit easier? This is called the diamond property. Which is that if I take one step in either direction, then I come back together in one step. Right, so rather than multiple steps. This is a lot more tractable. I just have to look at, for every term, what are the possible reductions I can go in either direction, and then see if I can bring them back together. Right, that's something I can actually do by induction. Okay, and then do we believe that the diamond property implies confluence in general, so many reductions? And we should double check these things, right? So I'll draw the little diagram. So from diamond property to confluence, if I have a bunch of reductions this way and a bunch of reductions this way, then of course I can bring each one together in one step, kind of going by induction down one side and induction down the other, right? We kind of carry it across. So doing these tilings is actually a little important because we'll see these things are more subtle than you think, right? And then boop, boop, boop. We finally bring it all together by transitivity, right? Chain them all together. Okay, so let's try, and I'll cut to the chase. So does the lambda calculus have this diamond property that if I take two reductions in two different directions, that I can bring them back together in one step? So I see some answers. Maybe some people have dealt with this before, or they just are very familiar with lambda calculus. So suppose I have something that could be a beta reduction. So of course, I could rewrite this to m with n for x. That's one step that I could do. What else could I do here? Well, I could reduce an m, and then that would be fine. right? So if I reduce this to lambda x dot m prime n, these do come back together in one step. I guess I could say 1 or 0 would be fine here. If I delete a step, that's also fine. But what if I reduce the argument? Then what happens, right? So clearly here, I can do one beta reduction step at the top and get m with n prime for x, right? And how does the term on the right catch up? A bunch of steps, right? Because this x might be used many times, and I have to repeat my reduction step for every time it's used. So this is a whole bunch of steps, right? So this is not the diamond property. It is something else that's much more unfortunate, which is weak confluence, which is usually the backbone of any confluence, which says if I take one reduction step in any direction, then they can join back together in many steps. Right? So this is something I can do. And I mean, there's a bunch of cases, but you can rule them all out. Right? And this is the main one that does duplication. Anytime you substitute, you'll duplicate. In general, erasure is fine, but this, maybe I turn one step into 5 steps. That's a problem. They say, well, maybe weak confluence. If it's weakly confluent, then do I have a confluent system in general? All right? Who here has heard of weak confluence? Has anyone heard of weak confluence? OK, some people have. So does weak confluence imply, this is sometimes called strong confluence by contrast. Does it always imply strong confluence? I see some nodding. You might think it's obvious. No. This is like the saddest thing. It doesn't. And I could go on. Like usually, it's non-termination really causes a problem. So certainly, you usually need termination or some other really fancy properties. And you'll prove weak confluence and then say, I have some other property that gets me confluence. But I like to do a little example, a little toy system that kind of shows that certainly weak confluence does not always imply strong confluence. And this is why I say you actually have to draw these tiling diagrams, because you'll look at it, and I see all the time in papers, people will say, yeah, I mean, this works, and it doesn't, for usually these reasons. So let's do a rewrite system for a coin flipping game. So I flip a coin. And it's in the air, and it flips between head and tails for a while. Right? So I've got one operation, which is it's flipping, and 2 constants, heads or tails. So if I'm flipping heads, then I'm still flipping, and now it's tails. If I'm flipping tails, then it's still flipping, and it's heads. And then finally, if I flip some coin, it might land. Right? So it flips some number of times, I don't know, and eventually it lands, and then it's on the ground, it stops flipping. Okay? So this system is weakly confluent. So what's an example? Suppose I'm flipping a heads, and 2 things could happen. I could keep flipping, and it turns over to tails, or I could land. Can I bring these 2 sides back together? Yeah, I could keep flipping again on the left, right? So the right-hand side is stuck. But I could flip again. I could say, well, this flip to head, and then that goes to head itself. And of course, head reduces to head in 0 steps. So this is OK. And there's a few other examples like this. So this is weakly confluent. Is it strongly confluent? No, because I could take instead, what if I did this? I said, I'll continue one more step, and I'll land. Stuck. They never come back together. So I can have weakly confluent systems that are not strongly confluent. Right? So never in your paper, if you need or want confluence, never say, oh, yeah, I proved this theorem, therefore it's confluent. It's like really easy to believe this, and it's unfortunately not true. Right? So that's one of the very sad things. So what do we do instead? And there's actually a lot of theory about these kinds of systems and how they work. So let me kind of bring up, I just want to remember the citation. Yeah, so the typical operational semantics is here. These are my rules. So the typical thing that happens most of the time, and is the easiest thing to do, so always try this first, is to look at these properties. And there's a thing called, I think that's going to escape on me. So there's a thing called an orthogonal rewriting system. So an orthogonal term rewriting system. So it's talking about the rules that we're using. So it's saying pick some rules that you want on whatever grammar of syntax you want. I don't really care. And then we're going to be talking about the reflexive transitive compatible closure of those reduction rules. Right, that's a term rewriting system. And it's orthogonal if it has these two properties. So is left linear and what does left linear mean? So in each of these reduction rules, I have some metavariables, right? And the idea is no metavariable appears more than one time. So what's an example of a non-left linear rule is one that would be really cute, right? If I have some equality comparison and I say give me two of the same term and then that goes to true. This is non-left linear because I'm saying give me two of the same syntax trees. Right? So this is not left linear. And, well, that's a really easy property to check. In all of my rules, on the left-hand side of an arrow, do you see the same n or m more than one time? Yeah? There's one more. That's the important one. So this is the first one. That's the easiest to check. You can pretty much look at them and say yes. Right? The other one, you still will, but I mean, it technically takes a little bit more work. This is, how is it phrased exactly? I'm trying to remember. Yeah, there are no critical pairs and has no critical pairs. So this is still an examination of the rules, but what does a critical pair mean? The idea is, did I leave up my, OK. I did not leave up my counter or my thing. But anyway, when we do reductions in a tree, there's basically three things that could happen if I have two separate reductions. Right? So I've got my whole syntax tree here. So there are three cases. The first case is I could be reducing in two separate places. Right? So I kind of, you think this is the root of the tree, and I go down to two different places, and I apply a rule at these two spots. There's clearly no interference or interaction between them. This is a trivial case. There's another case, which is I find a redex here, and then I can continue on and then find another redex here. So they're nested. That's the one we saw that broke the kind of diamond property, where I had one reduction kind of in the meta variable of another reduction. OK, that's fine. But another messy thing could happen. Right? What if I have something where essentially I've got this syntax tree, and I come down here, and I've got this. This is the root of the reduction rule, and it kind of looks at part of the syntax tree, but not the whole thing. Like, there's going to be some metavariable holes in it. And maybe within that matching, there's another rule that I apply. Right? And so, well, I'll just say these rules have no critical pairs. So if I apply one of these rules, is there any other rule that could gobble up some of the things? And it's kind of hard, I think, to see. Like, this clearly has nothing to do with an if, then, else, and vice versa. This doesn't say anything about functions and applications. But I could have another rule that looks like this, which is actually a very useful rule to have sometimes, which is if m then n1 else n2 applied to m prime. So if I have an if then else and I don't know how to resolve it yet because I have to figure out the Boolean, but these return functions and I apply those functions, then I might as well move the m in so maybe it can interact with the two branches. Right? So this could reduce to if m, then n1 applied to m prime, else n2 applied to m prime. So you can kind of maybe convince yourself this makes some amount of sense. Because what will happen if at the end of the day everything goes well, I get a Boolean, I will return either n1 or n2, which gets applied to m prime. Or m reduces to that same Boolean, and I'll just return n1 or n2 applied to that m prime in the body of the branch, right? But now this rule and this rule interfere with each other, right? And then you kind of have to argue, if you have something like this is actually a useful rule that's true most of the time and really useful to have, but is a critical pair, and so that's a big pain. So you don't get to just wave your hands. But this is just an example of something that is a critical pair with one of these rules. And there's like a bunch of other of these kinds of rules that you could have that kind of interfere and interact. So the reason why I bring that up, though, of course, is checking for critical pairs is we're kind of just looking at them and seeing if they interact. Usually don't sit down and draw the trees. But you can kind of eyeball it. And it'll give you a good idea for that. And, well, really the fact is, if ever I have two steps between any two rules, then it has to be wholly within one of the metavariables. Yeah?
So can I summarize
Yeah.
critical pairs being a given expression, you can only apply a single reduction rule?
It has to do with, in a sense, the syntax nodes, right? So let me draw out the syntax nodes. So you kind of, I think if you kind of have to visualize these things as a tree to really get them. So if I've got an if, I've got an application. Suppose this is an application to an m prime. And on the left is an if with three parts. I've got a true, and then a n1, and then a n2, right? So this is my critical pair. So basically, what if this was true? Then I would have two reductions. And what do the rules apply to? So one of the rule is applying, the outer one is applying to this, and then the inner one is applying to this. There's an overlap between the syntax nodes that are involved with one another. All right, that's what we're trying to avoid. And not having critical pairs is actually a really common thing, so it's worth looking for because it doesn't take you that long. And what is the primary result? Why do we care? There's a theorem which says all orthogonal, spelling is good, orthogonal term rewriting systems are confluent. And the proof is from Klopp. What's the year? I always forget the year. 1993 term rewriting systems. Writing systems. So that's a book that explains the whole term rewriting theory. Right? There's a whole bunch to cover that I can't cover. But this is one of the main results that's really wonderful because I get to look at this and say, it's left linear. There are no critical pairs. Therefore, lambda calculus is confluent. Therefore, beta conversion is the same thing as beta reducing to the two sides to the same reduct. That's really nice. I don't have to do any more work. Okay? So this is the one side of the coin, or once the first step is confluence. Right? Yeah.
When you say that you get this confluence property by
Yeah.
Feels like it.
Oh, it's still confluent, but for a different reason.
No. So my question is, if such rules are not strictly necessary but useful for something,
Yes.
that suggests you trade-off. If you can trade off between adding rules to make something else useful and making it easier to show confluence.
Yeah. Yeah.
What is the other thing you're trading off again?
Oh, well, you'll be able to relate fewer terms right here, so they'll get stuck all the time. Right? So for example, suppose that these are both functions that, I don't know, return false, right? Just like before. Then I should be able to prove that no matter what, if this returns, it returns false. And I can't do it right now, right? So if I have some complicated expression, so if I have if x, then lambda x, or lambda underscore false, else lambda underscore false, right? And I apply it to some m, I should be able to say that this is the same thing as an if then else that returns m in either case. I can't do that without this rule. And there's like a bunch of other, this is just the first thing to come to my mind. There's a bunch of things if you want to, especially if you want to, this is always useful. There's a bunch of others if you want to reason about call by value programs. You're going to get stuck all of the time for these kinds of stupid reasons. There's even more of them. And very few programs you'll be able to prove are similar without other methods. So if you add in these rules, you'll be able to prove way more programs are similar. And confluence is a little bit harder. But I mean, I guess that's probably why you're after that anyway. OK, so that's the first step, which is confluence. Now, I want to talk about standardization. I'll say less about that because I have less useful words.
Just for the mic, do you mind?
The question was, well, adding these rules makes confluence harder, so is there any benefit to doing so, right? It's a trade-off, or we're just making our lives harder for no reason. I'm grossly rephrasing, but that's roughly the gist. So there are reasons, right? We can prove more programs equal, and we have to pay the price a little bit. But you do get a lot of stuff for free just by, waving your hand in the direction of CLOP and then looking at your rules and saying, great, right? So that's the one step. I definitely want to talk about standardization. So I'll do that over, that's the operational semantics. That's that. I think I'll do my standardization right here. OK. So what is the standardization property? I think this one is maybe a little easier to see, but then harder to do. So standardization. Standardization. And as far as I know, this comes from much older terminology. We refer to these things up here as the operational semantics, right? And typically these days, you start with something like an operational semantics. Then we can derive the compatible closure, and then we can derive a rewriting system for equality. But originally, in lambda calculus, it went the other way. Church started with beta conversion, from which Church and Rosser proved confluence and this rewriting property. And then later they said, is there a standard order that we could pick? So maybe if we had computers, we could implement them. So they went in the reverse direction. So they said, oh, well, of course I can just do stuff anywhere. That's obvious. I took high school math. But is there a standard order that always gets me that same answer? Right? Do I need this total freedom of non-deterministically picking arbitrary redexes? Or can I just follow one, point me out to one or the other? So that's kind of why the terminology is what it is if I can generally reduce to a value, is there a same reduction in the standard order that gets me somewhere similar, right? And so the statement looks like this. If m reduces generally to a value v, well, I'll write what we hope. Then m in the operational semantics, so following the standard order of steps, also reduces to v. So that's intuitively what the theorem should say. It's not true. Why is it not true? So, well, what if I have lambda x, what we had something like not true? It's a good one. It's not true. So does this take any steps? No. But it reduces to lambda x dot false. I think you need a couple steps for that. So I can reduce to lambda x dot false, but I cannot use the operational semantics to do that because it's under a lambda. So it's annoying, but this is the actual theorem that does work. You say it reduces to a different value. OK, so I at least get something. And how are they related? They should be similar. I can say a little bit more about similarity this time. I may have reduced more here because I'm allowed to go under lambdas that I haven't actually called. So I may have to simplify w under lambdas a little bit more. So then it reduces to w such that, well, actually, I'm not going to do that. And w keeps reducing to v. Right? So if you have total freedom to reduce anywhere you want, and you get an answer, you get a value, then I can just run the program and get a value that's the same thing but a little less optimized inside of function bodies that you haven't called yet, things like that. Right? That's what this is saying. So I can still get a value. And one thing to note, are these two things similar? So what are the values? Well, if it's true, then, I mean, it can only reduce to true. It doesn't reduce to anything else. If those are similar. If it's false, it's false. If it's a lambda, then I can reduce in the lambda, but it's still going to be a lambda. It's never going to not be a lambda. I don't have any reductions, and this is what you would look for. Do I have a rule that turns a lambda into some other weird thing? That's scary. Don't do that, right? And this is a reason you'll lose kind of these standard properties. So don't do that. So this, if there are two values and one reduces to the other, then they're similar in this sense. And this is an advantage of just being very shallow about things. OK? And this is harder to prove in Confluence because we don't have a wonderful theorem from clock that we just get to use to make all of our problems go away. I can give you some hints on what I've typically done in the past to do this. There's definitely a bunch of literature doing this for the lambda calculus. I don't know how well it scales to other languages. But a good way to start thinking about it is, these are my standard reductions. And then I have some other reductions. So I want to talk about the difference between standard reductions that are in my operational semantics and the other stuff. Right? So I'll have non-standard reduction. Which is m, well, and I'll say this is a property. Sometimes I'll use this arrow. It's kind of like a wonky, it's not a straight tail, it's some other tail. Reduces to n, and it should have the property if and only if it is a reduction. Sorry, this is one reduction step. Right? So it is a reduction, and it is not a standard reduction. Right? And m is not a standard reduction. I don't want them to overlap. They're just different. You could take this as the definition, but often it might help to give this an actual inductive definition, like we had before. And then the property, the thing that you need to do is some commutation. Right? So if, and essentially the idea is, you'll find out that these standard reductions should never be able, or non-standard reductions should never be able to make something of value. So in some sense, if I have non-values over here, and I have values over here, then certainly I can take a step if it's not a value, and it might not be a value. And I can also take a step that's standard and convert it into a value. And the non-standard steps, well, they could be here, and they could be inside of values, but they never bridge the gap. And then values never reduce outside, right? A value never reduces to something that's no longer a value. These are properties you'll want your reduction system to have, right? And so here then, the thing that we're trying to prove is if I start with some non-standard stuff first and then do standard stuff second, let's do it in the other order. Right? So this is the commutation property. If m takes some non-standard steps to m prime, or let's do m1, and then that takes some standard steps to m prime, then I can do it the other way around. I start from the same m. I do my standard stuff first, m2, and then I do my non-standard stuff, m prime, afterwards. All right. So that's the tricky thing to prove, but that gets you standardization, as long as you know these bubbles work, right? Because I can use this to reorder all of the reduction steps. So it's standard reductions only first, then non-standard reductions afterwards. And then if this is a value, then that's a value. So I'm done. But do a bunch of steps and then do a bunch of more steps is really hard to do. So usually you can do it from something a little bit simpler, right? So instead, you can do something like this. If m reduces in many non-standard steps to m1, and then takes one standard step, right? So we're kind of saying reduce internally inside in weird places, and then take the standard step. This is sort of saying the non-standard reductions don't mess up your next one you're going to do. They're just elsewhere. They don't change the actual path to the main redux. Then we can go the other way, m, and typically you'll have maybe multiple standard things, because I literally could just be doing the next things that I'm going to do in the future. So those unlock and become now. Then that I get some other m2. And then this is many steps. This is many steps, beta m prime. So this is a little bit more tractable to prove, and it implies that one, which may not be obvious. So you might want to sit down and say, if I know this, just kind of like weak confluence didn't imply strong confluence. But if I can do it where I have many non-standard, one standard, can I kind of flop them around, say, just by induction on these arrows? Not worrying about what's going on, just can I look at the sequence and do it to generalize to many. So if you have this, then you can rewrite all of your standard reduction arrows, or all of your arrows to be standard followed by non-standard. And then we get a standardization theorem, because these will all be non-standard. Therefore, the fact that this is a value means that's a value. Right? Yeah.
For the standardization, I'm trying to understand the import, because if
Yeah.
double arrow maps to
Yeah.
is reflexive, then what's barring us from setting W to be M and then just doing like a no step? Yeah.
Because this has to be a value. So if you start with, yeah, this is why I say it has to be, otherwise it would be trivial. Yeah, exactly. You'd be like, we'll do nothing, and then there you go. So you actually have to use the standard steps to reach a value, which is the hard part. And after that, I stop caring, right? But you'll get that result anyway, so you might as well publish it, is the idea. But like you stop caring once you get that value. So you actually have to reach the value. That's the hard part. Now, this is a thing, and so I won't show the proof, but you can prove that that's much harder. If you really want to challenge, prove that this lambda calculus has standardization. But now I want to move on to the point. Why do we do these two things? It's like, OK, fine. If I have equality, I can say something about reduction. If I have reduction, I can say something about the operational semantics. So this is a really neat method to prove that this rewriting is equivalent to contextual or observational equivalence up there. So now we're going to prove that, well, the theorem is if m is beta eta equivalent, or just beta equivalent to n, then m is contextually equivalent to n. This is like what we care about, that the reduction rules actually say something about what the programs mean when we run them. OK? So proof. And this is finally not an inductive proof, the first one I think that I've ever done in this lecture series. Right? But it's shockingly maybe a short proof, which all the inductive ones are very short, or something's going wrong. And that's my experience in programming language theory. It's either a long inductive proof or a really short non-inductive proof, and never anything else. Let's do that. So I know, right? You tell me, you give me a derivation, m is beta convertible to n using rewriting rules. So I have to show that they're contextually equivalent, which means something about a whole bunch of contexts, right? So let C be a closing context. Suppose it's an arbitrary context. Then I know that C of M rewrites to C of N by compatibility. That's just by definition of these rewriting rules. If they're equal, then they're equal in all contexts by definition. That's inductively assumed. OK. So this is by def. Then what do I know? I know that they convert to similar things by confluence. So therefore, C of M reduces to, well, actually, what do we have to say? I think, let me double check the order of these. These are actually the harder proofs because they actually have to fit together. You don't just follow your nose. I just have to remember, once you get it, yeah, here we go. Blah, blah, blah. Yes, OK. So let me skip that step for now. Just reorder them so they're the obvious thing. OK, so you tell me that there's a context, it's a closing context. You tell me that M in that context reduces to a value. So such that C of M steps to some value. And now it is my obligation to show you a similar value that N steps to. OK. So now everything's in the right order. I've all my premises. OK, so let's restate there again. So I know that they are beta eta convertible in that closing context, because they are in every context, so why not this one? OK. Then I know that they convert to a similar term using only forward reduction rules. So they convert to some n prime. Oh, one more step to make it a little bit easier. So not only are they equal in that context, they're also equal to B. Right? There we go. That was the missing step. So not only is C of N equal to C of M, it's also equal to V, because just running a term counts as something you could do. So that means that C of N reduces to, well, I'll say some N prime that also V reduces to, right? And then as a property, I'll just say it out loud. You can check that if something's a value and it reduces, it's still a value. Right, that's a quick thing that you can check by the reduction rules. Can they ever turn something that's a value into not a value? If you have a rule that does that, it's probably going to cause a bug somewhere. So I'll say this has to be a value W. It has to be because values only reduce to other values. OK? So now that means that N in the context C can simplify to a W, which also means by standardization, so this is confluence. Then by standardization, that means N will take some steps in the operational semantics to a W prime, which keeps simplifying down to W. Yeah. OK. And then we need to check, are these two things, are they similar? Right? And so basically, if they're true, then they're just true, and a lot of these are reflexivity. If it's false, it's false. And if it's lambdas, lambdas only reduce to other lambdas. I don't care what happens inside the body of a lambda at all. I just left it opaque. So lambdas only reduce to lambdas. Therefore, W prime is similar to V. And therefore, they're contextually equivalent. Right? So this is, and we're at 12, this is a method of justifying some of these rewriting rules. But also, we want to talk about how programs behave, and we want to actually reason about program equalities. And we want that to say something about what the program does if they run it. And here's kind of a whole methodology that will work if, even without knowing anything about types or involving types at all. Right now, I'll kind of wrap up and foreshadow some stuff I'm going to talk about next time. So this is observational equivalence, and I erased my examples, but we had some examples before. Now we can say, right, that now we can say that, for example, the function lambda x and false x is equal to lambda x not true, right? A bunch of other properties, right? We can do these kinds of things, and we do that just by applying rewriting rules. But we haven't gotten to be able to say, for example, this one, that not x does nothing, right? So why is it equal to lambda x when it should morally be true? And the problem is, well, if I plug in bogus stuff for x, it's wrong, clearly. And so that says I can't just use arbitrarily syntactically correct programs, right? So the only restriction here is that the context has to be syntactically correct. It has to close over free variables, but otherwise I don't care. If I know about types, and I want to say, really, this should be a Boolean. Therefore, there's only certain values it could be. That means I have to limit the number of contexts that I get, but then more programs are equal, right? So this is what I wrote up there is a untyped contextual equivalence. If you have typed contextual equivalence, then this will be, well, I'll say a sort of form of a typed contextual equivalence of type bool, arrow bool. So if I know it's a bool arrow bool function, and I only use it in contexts that respect this, then these two will be equal. Right, and I don't have enough reductions, but I can add some more equalities that are true under these contexts. But there is a sort of trade-off. I just want to say that. One sec, I just want to say the trade-off, and then I'll answer the question. I will do a bunch of questions at the end, which is the kind of untyped. This is the untyped. Visually, I have a giant set of all the untyped terms, and I say some stuff about them. And in the typed setting, I have a much smaller set of typed terms, but I say a much bigger set of stuff about them. So there's a trade. I mean, both of these things are valuable in their own way, because I can do a lot more with the untyped, or I can talk about a lot more things with the untyped stuff, but my conclusions are weaker. If I limit myself to typed things, I get stronger conclusions, but I need to restrict my scope of things that I'm dealing with. And what I'm going to talk about next time is going to involve some of the logical relations stuff that Amal has been doing, but now doubled up so we can talk about equality. And it's going to involve a kind of system that's actually really fundamentally based on untyped stuff and then layers typing on top of that. So it can be really useful to know things already about reductions in properties of untyped terms, even though I only care about the typed ones, right? And it's fundamentally, this is going to be based on a whole bunch of things that came from Girard and Reynolds for dealing with polymorphism, parametricity, but are basically, you can try to pretend that they're typed, but they're really not. And it's so much easier if you just forget about typing for a moment, even though that's what we care about. And so sometimes having these properties, I've done certain proofs where I really needed confluence or standardization or properties about rewriting in order to talk about the underlying untyped terms. And then I built a model of those terms that maybe behave like typed ones, right? And that can be a helpful. So I want to conclude there before going on. But yeah, so now I will answer. I know there's some questions, so now I'll answer some questions. Yeah?
Why isn't the not x case? Why are they're both lambdas, right? Why are they already equal?
Why are they, what's that?
They're both lambdas. Why
Yeah.
are they already equal? Because they're both values, right?
Well, because so they are similar if I don't do anything with them. But here, all of these forms of equality are compatible, right? Which means, or they're congruences. If they're equal in all contexts. So that means any context you can plug these into, they have to give the same answer. So for example, lambda x dot true should not be equal to lambda x dot false, because the second I pass in any argument, I get different outputs, even though they're similar. Yeah. Oh, and the question was, they're both lambdas, so why aren't they equal, right, already? And they're similar, right? There's different notions of equality. This is a bit of a hack where you kind of bottom out, but we really want the notions of equality to then hold when we embed them into larger programs that can actually use these functions. Otherwise, we would say all functions, no matter what they do, are equal, including the reverse function, the identity function, the sorting function, the function that steals all your bank account information. These are all equal functions. Yeah, let me swap them out. Who cares, right? The world is your oyster, right? So we don't want to do that except kind of at the very end as a bit of a technical device. And the fact that once they're equal and they return as lambdas, or they return as just 2 lambdas, I will know that they're still equal. So then if I embed them in yet a bigger context and I ran them, those would still be similar. And if those have lambdas in them, I could embed that in an even bigger context and they're still equal, right? It kind of keeps being equal. We know that. But as far as writing our interpreter, it's enough to just write closure, right? And with the promise that if you take that closure and use it again, then you'll still never tell a difference, right? So that's kind of where we want to, just like in the logical relations, we don't just say all lambdas are equivalent, but the bodies have to be equivalent if somehow you use them in the future, right? And that's why this kind of comes up there. OK, so any other questions? I know we're not egregiously late, but I kind of wanted to go through this confluence and standardization stuff a little bit slowly because it normally doesn't get covered at OPLSS. But I use logical relations a lot in my work. I also use this a ton, more than I'd like to, because it's incredibly effective. The 1-2 punch of standardization and confluence just solves a lot of your problems when you're dealing with, when you're ever comparing 2 programs to say, do they do similar things? Yeah. Any other questions? No? All right. Then let's all go to lunch.